Good afternoon, everyone. I'm Zixi Wang from Xi'an Jiaotong University. It is my great honor to introduce our recent work about preferential diffusion model and multi-stream combustion problem. And I will introduce my work from these aspects. First, hydrogen is a very promising field because it is a carbon. Hydrogen is a very promising field because it is carbon-free and it has high laminar flame speed and high adiabatic temperature, which causes the problem like flashback and high NOx emission. And oxy-fuel combustion diluted with water vapor can solve this problem. So if the combustor is stabilized with three-stream with a separate injection of dilution, oxidizer, and fuel, so there is no flashback risk. And if the oxidant is oxygen, so there is no problem of high NOx emission. And there are also some modeling problems like preferential diffusion and multi-stream mixing problems. So the combustion model need to be tested and validated. And there are also some problem of finite rate chemistry with detailed mechanism. And most important part is high computational cost. And because the detailed chemistry has large numbers of species, so there are also many transport equations for each species. And because of different timescale and chemical state of each chain reaction, it is hard for ODE integration problem. So our goal is to develop high accuracy and efficient combustion model for combustor design. And FGM can achieve a good balance between computational cost and time efficiency. For example, FGM is based on the concept of flamelet. And because the structure of 3D flame is similar with the flame structure of 1D laminar flame, so we can calculate the laminar flame in advance with software like Chem1D, Cantaro, and ChemKing. And based on this laminar flame data, we can create a chemistry table based on this data with the function of some control variables. And after table interpolation, we can apply the table to turbulent flame. So we don't have to solve those so many species transport equation. We can only solve several governing equations of some control variables. And because the source turn and thermal physical parameters are tabulated in advance, so we don't have to solve these parameters when we calculate. So we can achieve a good computational acceleration. And there are also some problems with FGM. For example, first is preferential diffusion. And because the thermal diffusion coefficient is not equal to the mass diffusion coefficient, and it is especially dominant for hydrogen-enriched flame. And if the definition of control variables can be expressed as the linear combination of species mass fraction, so there are some additional diffusion term at the right-hand side of the control variables. And it is impossible to store all the species in chemistry table, so preferential diffusion term should be modeled. And so there are two ways to solve this problem. The first is we can calculate and store the summation of species partial derivatives with respect to the control variables. So there are some additional diffusion term for the control variables. and we can or we can calculate and store the summation of the linear combination of species in advance. So we only need to do the Laplacian operation to calculate the preferential diffusion term. And there are also some problems for multi-stream simulation. And because we usually use single mixture fraction to characterize the mixing between fuels and oxidant. However, for three-stream combustor, it is stabilized with a separate injection of three stream. So only high dimension flammlet can represent the mixing progress between fuel oxidant and dilution. And so one of the solutions is the oxidizer split method. And they use the variable W to represent the mixing between oxidizer and dilution. However, the control variable W is not always constant in the flammlet from this picture. And it is hard for table interpolation. So we need to map the value of W from 0 to 1 for each mixture fraction Z at the same value to make the data like a square. So so after this, the interpolation process can be more easier because W is always constant in the table. And it is better for beta PDF integration because those two control variables are independent. Or we can, and there are more complicated flame like this. For example, for four-stream flame, like with a separate injection of 2 fuel inlet and 1 dilution inlet and 1 oxidizer inlet with heat loss. And in order to include the heat loss, we can change the inlet temperature of 1D flame. And they realize the normalization by map the original table data to a cube to make each control variables independent and better for beta PDF integration. So our motivation is based on these concepts. First, the constant Lewis number is always adapted for multi-stream simulation, and there is no unified definition of multi-stream mixture fraction. And there are at most 4-stream problem is validated. And multi-stream can be expressed with the form of linear combination of species to model preferential diffusion. So our goal is to find a unified definition for multi-stream problem, which can also be applied to model preferential diffusion. So to find the definition of control variables in the form of linear combination of species mass fraction to model preferential diffusion for multi-stream with the definition of conservative scalar and their transport equation, if we can find the coefficient of beta in this equation to meet the definition of linear combination of conservative scalar. So we have the final definition of multi-stream like this, which can be expressed as the linear combination of species mass fraction. Because conservative scalar can also be expressed by linear combination of species mass fraction. So in order to get the exact value of beta, based on the definition of species and the composition of the stream, and with the element mass and element energy conservation and the mass conservation for each stream and each species, we can combine all of these equations in a matrix form. And because of the mass conservation, the coefficient vector A1 to AN plus 2 are linear dependent. And for coefficients of enthalpy, and they are it is not linear dependent with the rest of the coefficient vector. So we have the final condition of solution like this. And based on if we want to use enthalpy to express our definition, because sometimes we need the definition of enthalpy to characterize the effect of heat loss. So we can multiply a coefficient matrix C at the left side of A, and it is a row transformation of our matrix. So we have the final solution of the definition of mixture fraction for each stream. And so we have the final value of beta, which can be expressed like this. So with the definition of the transport equation for element mass fraction for so we after the linear transformation, we can have the final definition for each stream, and we also have the final preferential diffusion term like this, and this term can be modeled or neglected based on our cases. And this is the simulation setup of our case. And the whole computational domain has 3 inlets. And firstly is the fuel inlet with methane and hydrogen. And we also have the inlet of wet oxygen and the inlet of water vapor. And our cases are laminar flame because however, laminar flame can characterize the mixing problem between different stream and the preferential effect. And we finally have these 3 cases. And the first case is finite rate chemistry with the solver of DF low Markov form from D flame, and its transport model is mixture average. And we want to use this case to validate our data of FGM. And our FGM solver can, and we have 2 FGM cases to model the mixture between different stream and preferential diffusion with transport model like variable Lewis number and constant Lewis number. And this is the final result of our table. And different from the result of unity Lewis number, the table of non-unity Lewis number has a nonlinear manifold. And we have to change the order of variables because for control variable z at a fixed value, there are some mixing data. So after we permute the order of control variables, and we can do the interpolation to realize the linearization of the table. So finally, we have the result of constant Lewis number and variable Lewis number. And this is a simulation result of and from for temperature field and the species field, we can find out that the data of FGM is quite similar with the result of finite rate chemistry, and because the difference between different flame, the FGM with variable Lewis number has a better prediction. And for FGM with constant Lewis number, the maximum gradient of temperature and the equal line of hydrogen is a little bit higher compared with the finite rate chemistry result because it predicts the diffusion of the hydrogen maybe a little bit slow. So in a conclusion, FGM results are consistent with the finite rate results. The definition of the multi-stream is correct. So based on conservation equation, we got a unified definition for each stream. And variable Lewis number has better prediction of temperature and species compared with constant Lewis number. The definition of multi-stream is validated by Leibniz cases, and the result shows that the definition of FGM is correct. And that's all for my presentation. Thanks for your kind attention.